universe is vast, colossal, ancient, full of secrets yet to be unraveled. Amidst the thousands of stars that shimmer in the black velvet of the cosmos, some are similar to our own sun. Around them, planets orbit, silent, unseen, waiting to be discovered. In recent decades, humanity has taken bold steps into this invisible frontier, unveiling an astonishing diversity of alien worlds. Some of them are gas giants spinning beside scorched stars. Others are rocky infernos or frozen deserts, orbiting their suns too closely or too distantly to support anything we might call familiar. And then, among all these exotic spheres, a name quietly emerged: Kepler 22. A world located in what scientists call the habitable zone, the not too hot, not too cold region around a star where conditions might be just right for liquid water to exist. It was one of the first such planets ever found beyond our solar system. A planet that sparked global curiosity and whispered a simple question: could this be a new Earth? The story of Kepler 22b begins with the Kepler Space Telescope, a revolutionary observatory launched by NASA in 2009. Unlike traditional telescopes that capture sweeping images of the night sky, Kepler had a singular mission: to stare, unblinking, at a single patch of stars and look for dimming patterns that might suggest the presence of orbiting planets. And on December 5th, 2011, the announcement came. A new exoplanet had been confirmed, orbiting a sun-like star in the constellation Cygnus, roughly 620 light-years away from Earth. It was dubbed Kepler 22b, the 22nd star system cataloged by the telescope, and the first to reveal a planet in its habitable zone. This moment was historic. For the first time, humanity had found a planet beyond the solar system that was not only roughly Earth-like in temperature, but also revolving around a star not unlike our own. Though we still knew little, Kepler 22b became a symbol of potential, the first in a new era of discovery. Kepler 22b orbits a G5-type star, slightly smaller and cooler than our Sun. This star, known simply as Kepler 22, lies in the direction of the Swan, Cygnus, a familiar constellation in the northern hemisphere. While it's about 10% smaller than the Sun and emits a bit less light, its overall characteristics are comfortingly familiar. The planet itself completes one full orbit every 289 Earth days, a year slightly shorter than ours. This places it comfortably within its star's habitable zone, at a distance that allows temperatures to potentially support the presence of liquid water. But while the host star gives us hope, the real mystery and fascination lies in the planet itself. Let's be clear, Kepler 22b is not an Earth twin, it's a distant cousin at best, and perhaps something stranger still. Based on the depth of its transit, the amount of light it blocks when passing in front of its star, scientists estimate that Kepler 22b has a radius about 2.4 times that of Earth. That's a considerable size jump. In terms of volume, it's roughly 13 times bigger than our planet, yet its mass remains unknown. We have no direct measurement of its weight, which means we can't say for certain what it's made of. Is it a giant rocky planet, like a scaled-up Earth? Or is it a miniature Neptune, shrouded in thick gas layers with a dense, possibly icy core? Both are viable models. This ambiguity is key. If Kepler 22b is predominantly rocky and has a thin atmosphere, it could be one of the most promising locations for life beyond Earth. But if it's a gas-dominated world with crushing atmospheric pressures and no solid surface, its Earth-like orbit might be misleading. This is the duality that defines Kepler 22b: familiar, yet unknowable; a mirror, yet a mystery. Based on its distance from its star and the type of radiation it receives, Kepler 22b's surface temperature could be around 22 degrees Celsius, a pleasant 72 degrees Fahrenheit, if it has an atmosphere similar to Earth's. But that's a colossal if. A dense, carbon-rich atmosphere could trap heat, creating a runaway greenhouse effect like Venus. A thin atmosphere might not insulate the planet at all, rendering it frigid. And of course, a deep gaseous envelope might mean there is no true surface to speak of, just deeper and denser layers of hydrogen and helium. Interestingly, some models suggest that Kepler 22b could be an ocean world, a planet covered entirely by deep global seas, hundreds of kilometers deep, deeper than any trench on Earth. If so, then beneath those waters might lie hydrothermal vents, warmth, and the right chemistry for life to take root. Much like life may have originated in Earth's ancient oceans. Could there be waves crashing on unseen shores, or only endless aquatic twilight stretching over a hidden abyss? When we speak of habitability, we tend to imagine Earth-like conditions, a rocky surface, a temperate climate, breathable air. But habitability may be a broader concept than we ever imagined. Kepler 22b could support microbial life, or even complex aquatic ecosystems, if its conditions are right. But there's also a darker possibility that it's lifeless, that its oceans, if they exist, are sterile, or that it's enveloped in toxic gases, or has a core of rock covered by crushing kilometers of ice and fluid where light can never reach. These possibilities show us the limits of current technology. We can detect planets, estimate their size and orbit, and dream of their landscapes, but we cannot yet see them directly. Every image of Kepler 22b you've seen is an artist's impression, informed by physics and creativity alike. We stand on the edge of understanding, peering into the dark. One of the great challenges with Kepler 22b is the lack of direct atmospheric data. Unlike closer exoplanets whose atmospheres can be studied through spectral analysis during transits, Kepler 22b is simply too far and too dim for current instruments to analyze in detail. But speculation is not without value. Based on its size, researchers have proposed several models for its interior and structure. Some suggest a thick envelope of water and ice over a silicate metal core. Others propose a more Earth-like layout with a mantle, crust, and surface oceans. There's even the tantalizing idea that Kepler 22b might possess a moon, a massive, possibly habitable exomoon orbiting the larger planet, shielded from harsh radiation, warmed by tidal forces. Such a scenario, while still speculative, opens the door to an entire system of interest. Not just a planet, but perhaps a family of worlds. At present, no spacecraft is en route to Kepler 22b. At 620 light-years away, even our fastest probes would take tens of millions of years to arrive. But that doesn't mean we're blind. New telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope may one day allow us to characterize exoplanet atmospheres at greater distances. If a future generation of instruments detects chemical signatures like oxygen, methane, or water vapor on Kepler 22b, it would be a milestone for science and a quiet revolution in how we see the cosmos. Some even imagine a more distant future when interstellar probes, perhaps propelled by solar sails or fusion engines, could travel to systems like Kepler 22. It would take centuries or millennia, but the dream endures. The discovery of Kepler 22b was not an isolated event. It was the first confirmed habitable zone exoplanet, but it ushered in an avalanche. Since then, thousands more have been found. Super-Earths, mini-Neptunes, and rocky exoplanets in their stars' habitable zones now fill our databases. Some, like Kepler 452b, are even more Earth-like in certain ways. Others, like TRAPPIST-1d and TOI 700d, orbit dim red dwarfs, where the rules of habitability may be entirely different. Yet Kepler 22b remains iconic, a first glimpse, a symbol of what's possible. It taught us that planets like Earth may not be rare, that life perhaps is not an anomaly, but part of the fabric of the cosmos. Imagine for a moment standing on the surface of Kepler 22b, if such a surface exists. The sky might be blue or green or purple, depending on its atmosphere. Its sun, Kepler 22, would shine less brightly than ours, casting a gentler light. Perhaps you'd be standing on a rocky coast, watching alien waves roll in from an endless sea. Or maybe you'd be floating in a deep ocean, with nothing beneath but the quiet pull of gravity and the whisper of unknown currents. Above, the sky might shimmer with clouds made of vaporized elements foreign to Earth. And all around, silence, time, infinity. Kepler 22b may not be Earth 2.0, but it reminds us that the universe is a gallery of worlds. Some will be familiar, others will defy understanding, but all of them, every last one, tells us something about our place in the grand design. As we sit here on Earth, spinning in our own orbit around the sun, we look up at the night sky and wonder. Kepler 22b remains far beyond our reach, its light having traveled for 6 centuries before touching our telescopes. And yet, in a strange way, it is close, not in distance but in meaning. It reflects our hope, our hunger to explore, and our deep yearning to not be alone. Whether it harbors oceans or deserts, clouds or storms, life or silence, it matters. Because the discovery of Kepler 22b didn't just change astronomy, it changed how we see ourselves. Who knows what awaits among the stars? The answer, perhaps, lies on a blue world far away, waiting patiently for us to find our way home. But Kepler 22b was just the beginning. 3 years later, our gaze shifted once more, this time even farther into the galaxy. Another signal, another world. The universe is an artist, crafting celestial bodies in forms we could scarcely imagine. Some planets are vast and searing, locked in infernal proximity to their stars, while others are frozen giants drifting in the darkness. But now and then, the cosmos presents something truly unusual, something that defies our expectations and forces us to rethink what is possible. One such planet is Kepler 413b, a world that orbits 2 suns, not in a steady, predictable manner, but with an unusual wobble. It is a world of instability, of shifting seasons and chaotic climates, a world where the sky itself tilts unpredictably. This exoplanet challenges our understanding of planetary motion and raises a compelling question. Could such a dynamic world ever support life, or is it doomed to be an ever-changing, inhospitable wasteland? This is the story of Kepler 413b, a planet that refuses to move in a straight line, a celestial body unlike any we have ever encountered. Kepler 413b was discovered in 2014 by NASA's Kepler Space Telescope, the same revolutionary instrument that had already unveiled thousands of exoplanets hidden in the cosmos. But this planet was unlike the others. At first, astronomers struggled to detect it. While most exoplanets follow a predictable transit pattern, regularly passing in front of their stars and dimming the light in a steady rhythm, Kepler 413b behaved strangely. For 180 days, there was no sign of the planet. It was invisible to Kepler's precise instruments, hidden somewhere beyond its usual trajectory. Then suddenly it reappeared, crossing in front of its star system in a brief, erratic transit. And just as quickly as it had arrived, it vanished again, not to be seen for another 800 days. This was an unprecedented discovery. Something was causing Kepler 413b to shift in its orbit, making it unpredictable and difficult to track. What was happening? Why was this planet behaving in such a strange manner? To answer these questions, scientists needed to take a closer look. Kepler 413b orbits a pair of stars, a binary system composed of an orange dwarf and a red dwarf. These 2 stars are locked in a tight orbital embrace, circling each other every 10 days. This alone is remarkable. Binary systems present a complex gravitational environment, making planetary formation more challenging. But what makes Kepler 413b even more unusual is the extreme tilt of its orbit. While most planets maintain a stable alignment with their stars, Kepler 413b's orbit is misaligned, tilted at a steep angle, and this tilt isn't constant. It wobbles dramatically over time, shifting the planet's orientation in unpredictable ways. This phenomenon, known as precession, is incredibly rapid compared to anything seen in our solar system. For comparison, Earth's axial precession, the slow wobble that changes the orientation of our planet's tilt, takes about 26,000 years to complete a cycle. Kepler 413b, on the other hand, wobbles on a time scale of only 11 years. That means its seasons, its climate, and even the way the stars appear in its sky could change dramatically in just a few years. Imagine standing on the surface of this world, looking up at the sky. One year, the two suns might rise and set in a relatively normal pattern. A few years later, the sky could look completely different, with the stars appearing in strange and unfamiliar positions. The suns could shift unpredictably, altering the climate and plunging the world into extreme, chaotic seasons. This is a planet where nothing stays the same for long. Kepler 413b is a super Neptune, a gas giant approximately 65 times the mass of Earth. With a radius about 2.5 times that of Earth, it is much larger than our home planet, yet smaller than Saturn or Jupiter. But despite its size, scientists still don't know exactly what kind of planet it is. One possibility is that Kepler 413b is a gas giant like Neptune, with no solid surface and a thick atmosphere of hydrogen and helium. If so, then it is unlikely to support life, as any spacecraft or probe would simply sink into its swirling clouds. However, some researchers believe it could be a mini Neptune, a world with a thick atmosphere, but also a solid core, possibly covered in deep oceans or ice. If this is the case, then the planet might have extreme weather patterns, with violent storms, powerful winds, and shifting cloud formations driven by its unstable orbit. And then, there is the more exotic possibility that Kepler 413b could be an ocean world, a planet covered entirely in liquid water, with no land masses to break the endless waves. If it has a dense atmosphere, it might have clouds and rain, creating an alien water cycle completely different from Earth's. But even if there are oceans, could anything survive here? The answer is complex. At first glance, Kepler 413b seems far from hospitable. Its extreme axial tilt, rapid precession, and shifting climate would make it nearly impossible for Earth-like life to take hold. If the planet has a thick atmosphere, it could experience sudden and violent temperature swings, with periods of intense heat followed by extreme cold. But what if life on Kepler 413b adapted to its chaotic environment? In recent years, scientists have discovered organisms on Earth that can survive in conditions once thought impossible. Some microbes thrive in acidic lakes, in boiling hydrothermal vents, or in the deep darkness beneath Antarctic ice sheets. Could similar life forms exist on a world as unstable as Kepler 413b? If Kepler 413b has liquid water, whether in the form of oceans or underground reservoirs, it is possible that hardy extremophiles could survive there. Deep-sea hydrothermal vents on Earth provide energy to entire ecosystems in total darkness, relying not on sunlight, but on chemical reactions. If Kepler 413b has a similar system beneath its surface, life could exist even without stable seasons or predictable temperatures. However, there is one major complication. Kepler 413b orbits too close to its binary stars. It completes an orbit in 66 days, meaning it is much closer to its stars than Earth is to the Sun. This makes it highly unlikely that it lies within the traditional habitable zone, the region where liquid water can exist on a planet's surface. If Kepler 413b is a gas giant, it is unlikely to host life itself. But what about its moons? One of the most exciting possibilities for exoplanet habitability is the presence of large moons around gas giants. In our own solar system, some of the most intriguing candidates for extraterrestrial life are not planets but moons, such as Europa, Enceladus, and Titan. If Kepler 413b has large moons, they could be more stable than the planet itself, They might have their own atmospheres, oceans, or even continents. A moon with a thick atmosphere and liquid water could be a prime candidate for habitability, even if the planet it orbits is inhospitable. So far, we have no direct evidence of moons around Kepler 413b, but that doesn't mean they don't exist. Our ability to detect exomoons is still in its infancy, and with better telescopes in the future, we may one day confirm their presence. If such a moon were found, it could completely change how we think about life in the universe. At present, Kepler 413b remains a mystery. We know it exists, we know it wobbles, and we know it is massive, but beyond that, much is still unknown. Future telescopes, such as the James Webb Space Telescope, could help analyze the planet's atmosphere, searching for signs of water vapor, methane, or other chemical signatures that could hint at its true nature. Meanwhile, astronomers continue to study other tilted planets in the galaxy, searching for patterns that might explain Kepler 413b's strange behavior. Could there be other planets out there that wobble like this? Or is Kepler 413b a true anomaly? One thing is certain, the universe never ceases to surprise us. With every discovery, we realize just how strange, chaotic, and wonderful the cosmos truly is. And somewhere out there, 2,300 light-years away, Kepler 413b continues its erratic dance, a reminder that in this vast, mysterious universe, even the planets refuse to follow a straight path. Who knows what else we'll find next? Among the countless stars shimmering in the darkness of space, many host their own planetary systems. Some worlds are scorched by the relentless heat of their stars, while others are locked in perpetual twilight and ice. Yet hidden within this cosmic grandeur may lie planets whose conditions bear a striking resemblance to our own Earth. On these planets, vast oceans could stretch as far as the eye can see, clouds might glide across the sky, and flashes of lightning could illuminate distant horizons during thunderstorms. It's tempting to believe that life has found a way to flourish there, just as it once blossomed here on Earth, in its oceans, forests, deserts, and at the icy poles. And yet, life itself remains one of the most astonishing, complex, and mysterious phenomena in the universe. Despite thousands of years of study, we still lack answers to many questions. The biggest being, does biological life exist anywhere beyond Earth? And if it does, where should we look for it? And how would we recognize it? In pursuit of answers, humanity has undertaken extensive investigations of planets circling distant stars, exoplanets that could potentially resemble our own world. Astronomers have already confirmed the existence of thousands of these enigmatic objects. Some orbit old, faint stars, while others circle young giants that emit overwhelming energy. Yet in evaluating each new world, scientists specifically look for signs of water, an essential suite of chemical elements, and moderate temperatures, the very conditions that make life possible as we know it on Earth. To gauge how Earth-like a particular exoplanet might be, researchers have developed a special measure known as the Earth Similarity Index, ESI. Let's explore what it is, how it's used, and how it relates to one of the most intriguing exoplanetary discoveries to date, Kepler 452b. The Earth Similarity Index, ESI, is among the simplest and most common tools for a quick assessment of how closely an exoplanet's basic characteristics match those of Earth. At its core, the ESI involves two key parameters, the first being surface gravity. It's calculated from a planet's mass and radius. If the gravity is significantly higher or lower than Earth's, organisms similar to those on our planet might face serious challenges in terms of body structure and metabolism. The second factor is temperature, which is derived approximately from the planet's distance to its star and the star's brightness, or luminosity. If the temperature is too low, water remains locked in ice. If it's too high, water can only exist in vapor form. Both extremes are unfavorable for Earth-like life. Combining these parameters yields a single score that reflects the degree of similarity to Earth. However, this metric has clear limitations. it does not account for other key characteristics, such as stellar activity and orbital nuances. Red dwarfs often unleash powerful flares that can strip away atmospheres and intensify radiation exposure, while massive stars, like Sirius or Vega, live too briefly for complex life to develop. Orange and yellow dwarfs, such as our Sun, are generally considered more promising hosts. If a planet orbits too close to its star, it can become tidally locked, leaving one side perpetually scorched while the other remains in darkness and cold. Conversely, if it lies too far away, it risks freezing beyond the habitable zone. Despite these drawbacks, the ESI is a convenient, quick filter because calculating it requires only basic information about a planet's mass, radius, and orbit. Earth naturally serves as the gold standard by which we judge conditions capable of supporting life. Kepler 452b was discovered by NASA's Kepler Space Telescope, launched in 2009 to detect planets around other stars via the transit method. The principle is simple. When a planet crosses the face of its star, it blocks a small portion of the star's light, causing a slight dip in brightness. By measuring these dips, astronomers can estimate the planet's orbit and approximate size. In 2015, NASA scientists announced the discovery of a planet designated Kepler 452b. Why did it spark such excitement? The star Kepler 452 is very similar to our Sun in spectral class, and Kepler 452b orbits within the habitable zone, far enough from the star that, if it has a suitable atmosphere, liquid water could exist on its surface. Additionally, its radius turned out to be only about 1.5 times larger than Earth's. All of this led researchers to speak of potentially Earth-like conditions. Kepler 452, the planet's host star, is located about 1,400 light-years away in the constellation Cygnus. Its spectral type is G2, practically the same as our Sun. However, astronomers estimate that Kepler 452 is about 1.5 billion years older. This makes the system particularly interesting. If the exoplanet has remained in a habitable zone for so long, life there could have had more time to arise and evolve, assuming other conditions were favorable. Kepler 452's mass and luminosity are only slightly higher than the Sun's, and its surface temperature is comparable to solar values. In terms of chemical makeup and evolutionary path, Kepler 452 follows a similar pattern, but is at a more advanced age. Scientists often refer to such stars as solar twins, pointing to their significance in the quest for life-bearing worlds. It's believed that Kepler 452b completes one orbit in around 385 Earth days, meaning a year there lasts about a month longer than ours. Calculations show its orbital radius is just a bit larger than Earth's, placing it slightly farther from its Sun-like star than we are from ours. Thanks to Kepler 452's slightly greater brightness, the planet may still receive roughly Earth-like levels of energy, maintaining a similar energy balance. Of course, there are many unknowns. We lack precise data on heat distribution, axial tilt, and possible moons. Even so, the mere fact that this planet's year is close to 385 days, coupled with its location in the habitable zone, sparks the imagination. We can't help but picture what it would be like if we were there, how much longer the seasons might last, and how different their cycle might be. Kepler 452b's radius is about 1.6 times larger than Earth's. On one hand, this leaves open the possibility of a solid surface rather than a purely gaseous envelope. On the other, such a larger radius may indicate that the planet is closer to a mini-Neptune or a super-Earth with a thick atmosphere and strong gravity. Determining its mass is difficult, but models suggest it could be 5 or 6 times Earth's mass if it's mostly iron and rock. Its internal structure remains a mystery. It could possess a hot iron core surrounded by a silicate mantle and crust, or perhaps it contains extensive layers of ice and water if it formed farther from its star. Its substantial size increases the likelihood of a dense atmosphere, yet we don't know if this atmosphere is breathable, toxic, scorching like Venus's, or something entirely different. As soon as scientists announced the discovery of Kepler 452b, media outlets splashed headlines about Earth's twin and New Earth 2.0. However, experts advise caution. While the orbit and star of Kepler 452b appear promising, countless factors ultimately decide whether a planet can be hospitable to life. A key question is the atmosphere. If a runaway greenhouse effect has developed, the planet may be superheated like Venus. Conversely, if the atmosphere is too thin, stellar radiation could overwhelm its surface, or the water could simply evaporate into space. A planet's magnetic field, crust composition, and tectonic processes are also critical, but currently unknown. Even so, the fact that it lies in a habitable zone around a sun-like star gives hope for favorable conditions. Since the Kepler mission, other space observatories and ground-based telescopes have added Kepler 452b to their watch list. Instruments like the Hubble or ground-based Very Large Telescope (VLT) systems can at least refine what we know about its star and look for subtle gravitational effects. However, a full spectroscopic study of the exoplanet's atmosphere is still extremely difficult. Kepler 452b is simply too distant, and its star not bright enough for current technology to analyze in detail. Still, the future holds promise. Next-generation telescopes, such as the James Webb Space Telescope, and planned giant Earth-based observatories boasting mirrors over 30 meters in diameter with advanced coronagraphs may eventually reach the precision needed to probe certain atmospheric traits of Kepler 452b. Detecting water, oxygen, or methane in its spectral data would be an exciting hint of biological activity. This work is daunting, but technological breakthroughs over the past decade inspire optimism. If Kepler 452b has indeed sustained a stable climate for hundreds of millions or even billions of years, evolutionary processes akin to those on Earth might have had more time to unfold. Since its star is older than the Sun, this world could have had a longer window to develop, or conversely, to run out of resources. Hypotheses abound, but none can replace the certainty that direct observations might bring. Then again, life on this planet, if it exists, might be drastically different from our own biosphere. There is no guarantee of photosynthesizing plants or carbon-based chemistry. Life could have found an entirely different path. Nonetheless, such possibilities fuel advancements in astrobiology, inspiring improvements in our search techniques for habitable worlds, and guiding us to learn how common Earth-like conditions might be throughout the cosmos. The idea of sending an expedition to Kepler 452b is mesmerizing, but at 1,400 light-years away, it lies beyond the reach of any technology we currently possess or might have in the near future. Even traveling close to the speed of light, the journey would take well over 1,000 years. Science fiction, however, loves to explore concepts of generation ships or revolutionary travel methods, keeping the dream alive. For humanity, the very existence of such a nearly Earth-like planet at that distance highlights the vastness of the universe. If these worlds are real, then perhaps somewhere among them are beings who have passed their own prehistoric era, discovered science, and built telescopes to look for fellow, intelligent life. This thought inspires us to push research further, never losing hope that we'll someday gather more direct evidence of life around the corner. Essentially, Kepler 452b is but one among thousands of exoplanets, yet it vividly illustrates a compelling idea. There are worlds out there that might be very much like ours. Each system, however, has its own story, and each planet its unique conditions. Observations of this distant super-Earth reveal how relatively small differences in radius and mass can profoundly alter a planet's fate. Perhaps it's home to temperate climates, or perhaps it's scorched by unbearable heat or beset by endless storms. Still, Kepler 452b's discovery bolsters our view that Earth is not a singular exception, but rather one of many celestial bodies capable of sustaining life. Direct data on its atmospheric composition, surface temperatures, or magnetic field remain a matter for the future. Yet even now, this planet expands our horizons, sets the stage for new missions, and drives scientists to search more intently for second Earths. One day we might find not just one, but dozens of potentially habitable planets, each with its own remarkable tale of how life can flourish among the stars. If you enjoyed this video, don't forget to give it a like and subscribe to the channel. It's the best way to show your appreciation for my work and inspire me to create more exciting content for you. Throughout its long history, Our Earth has proven time and again that the cosmos can be home to worlds drastically different from what we know. Beyond the familiar boundaries of the solar system lie the so-called exoplanets, celestial bodies orbiting stars other than our Sun, often at inconceivable distances. Merely half a century ago, the very existence of these distant planets was mostly theoretical. Now, thanks to modern technology, astronomers discover hundreds of new ones each year. Many of these newly found worlds are hot Jupiters, orbiting so close to their stars that they reach searing temperatures. Others may be cold, icy orbs drifting in the darkness of their outer systems, forever locked in frigid isolation. Then we have the truly exotic cases with extreme temperature swings, toxic atmospheres, or even surfaces made of unusual materials. Today we will focus on one of the most remarkable examples from this cosmic abundance, a planet known as 55 Cancri e, located in the star system 55 Cancri. This so-called diamond planet in super-Earth stands out for its intense conditions and for fueling bold hypotheses about the interplay of fiery geology and high-temperature chemistry. It is difficult to find a more striking illustration of how far a planet's environment may deviate from the familiar Earth-like image. Although 55 Cancri e orbits so close to its star that its surface might literally be melting, hints of volcanic or magmatic activity combined with the possibility of a carbon-rich interior to spark constant scientific intrigue. In this discussion, we will shed light on the captivating world of 55 Cancri e, part of the famed 55 Cancri system, and see just how bizarre planetary conditions can become once we move beyond the bounds of the solar system. More than half a century ago, star 55 Cancri, cataloged also as Roan Cancri, had already been relatively well studied, being only about 41 light-years away, which is close by cosmic standards. Yet the presence of planets orbiting this star wasn't conclusively proven until the 1990s, when astronomers systematically searched for exoplanets using Doppler spectroscopy, detecting minuscule variations in a star's radial velocity caused by the gravitational pull of orbiting planets. The first planets in the 55 Cancri system were identified in the late 1990s. Not long afterward, researchers realized that the system might contain at least 4 or 5 significant objects. Ultimately, around 2004, evidence pointed to the existence of the super-Earth designated 55 Cancri e, and that discovery became one of the key findings that demonstrated just how unusual short-period planets close to their stars could be. This object quickly rose to fame when some astronomers proposed the possibility of a diamond-rich interior. The interest only grew as subsequent refinements were made to its orbital parameters and physical properties. Scientists observed the planet's transits, which helped refine estimates of its radius and mass. Each new measurement spurred fresh speculations about its internal structure. Combined with the fact that 55 Cancri is relatively easy to view from Earth, in the northern constellation of Cancer, these discoveries turned 55 Cancri e into a prime target for exoplanetary study campaigns. By current estimates, 55 Cancri e is classified as a super-Earth. Its radius is roughly twice that of Earth, around 1.9 to 2.0 Earth radii, while its mass appears to be about 7 to 8 times Earth's. Such values yield a considerable overall density and led to the hypothesis that the planet might be extremely rich in carbon, potentially containing so much carbon that it could harbor enormous quantities of diamond in its depths. This striking idea captured public and scientific attention alike, since previously the concept of a diamond-laden planet seemed the stuff of science fiction. The story gained further momentum when calculations suggested that if the planet's mass is about 8 times Earth's, while its radius is only about twice Earth's, its density far exceeds Earth's, but remains somewhat below that of pure iron or other heavier elements. By comparison, our Earth's radius is about 6,370 kilometers, whereas 55 Cancri e's could be approximately 12,000 kilometers. Meanwhile, having 7 to 8 times Earth's mass would result in a gravitational force likely 2 or 3 times stronger than Earth's. A human visitor, if one could exist there at all, would thus experience crushing gravity. Yet even that would be overshadowed by the unimaginable heat that scorches the planet's surface. Scientists propose that 55 Cancri E orbits extremely close to its star, which itself is a bit smaller and cooler than our Sun, but still emits enough radiation to fry any nearby object. The planet's orbital period of around 18 hours, some studies say about 17, but either way extremely short, results in searing exposure to its star's energy. As a result, surface temperatures are thought to soar to between 2,700 and 3,000 Kelvin, above 2,400 degrees Celsius. Under these conditions, nearly all silicate rocks and metals would melt, forming magma oceans and even vaporizing minerals. Some astronomers propose that carbon might form extensive diamond regions in the planet's mantle, although this remains very speculative. Another possibility is that 55 Cancri E is more or less Earth-like in its composition, simply packed with heavier elements, with an iron core and a silicate mantle that is superheated near the surface. Either way, given the extreme heat, the planet's outer layers may not have anything resembling stable terrain. Instead, there could be a roiling expanse of molten rock, turning 55 Cancri A into what some call a lava planet. The earliest detections of planets in the 55 Cancri system relied on measuring the star's radial velocity variations. Observers at facilities including Lick Observatory and the Keck Observatory eventually confirmed the presence of multiple large bodies around 55 Cancri. However, the super-Earth 55 Cancri E remained elusive until improved instrumentation raised our capacity to detect modest-sized planets close to their stars. When the planet was identified around 2004, it drew attention as one of the tightest orbiting super-Earths known at that time. Observations with the Spitzer Space Telescope in the infrared allowed scientists to witness the planet's transit and refine its radius. Not long afterwards, speculation about a diamond planet captured the imagination, though direct evidence for such diamond-laden layers remains absent. Nonetheless, the prospect of unusual carbon-based chemistry spurred interest well beyond the scientific community. Telescopes such as Hubble made attempts to glean further data, particularly concerning any atmosphere the planet might hold, by searching for spectral signatures during transits. Results have been mixed, leaving the question open as to whether 55 Cancri E retains any gases at all at such punishing temperatures. Recent research with the James Webb Space Telescope holds the promise of clarifying the composition of its upper layers, assuming they exist. Talking about surface features on 55 Cancri E must be done carefully, given the inferno on its day side that can exceed 2,000 degrees Celsius. Most materials would liquefy at such temperatures, creating magma seas, heavy element vapors, and clouds of silicate dust swirling in the heat. Some astronomers suggest that one side of the planet faces the star more or less consistently, typical of tidal locking, but radial velocity data and other measurements imply that 55 Cancri E might instead occupy a more intricate spin-orbit resonance, perhaps rotating in a way that regularly exposes different regions to the star's intense energy. As a result, planetary days or nights might spawn cataclysmic volcanic events whenever lava breaks through and vents are created. The daytime hemisphere, inundated with stellar radiation, could generate mineral evaporation, while the cooler hemisphere re-solidifies these vapors or channels them underground. Some models even discuss the possibility of stone rain, in which silicate droplets condense out of superheated clouds. Though these concepts might seem far-fetched, certain theoretical studies suggest that, at extreme temperatures and pressures, planetary surfaces can behave in ways wholly alien to the volcanism we see on Earth. A crucial debate involves whether or not 55 Cancri has an atmosphere. Logically, with a surface that hot, one would expect any lightweight gas envelope to have been stripped away by the star's radiation. Yet the planet's estimated mass, on the order of 8 Earth masses, indicates a gravity that may retain heavier elements. Some scientists propose that 55 Cancri E might have an atmosphere composed of silicate vapors, metal oxides, or other heavy species, rather than the hydrogen-helium envelopes typical of gas giants. The star 55 Cancri bombards this world with potent stellar winds, so any original atmosphere likely evaporated eons ago. Meanwhile, if the planet has an internal mechanism that outgasses minerals or volatiles, that might partially replenish or cycle certain gases. Additionally, the possibility of heat redistribution from day to night side, if the planet's interior is geologically active, has led to a variety of climate or weather models, each pointing to a truly infernal system of heat transfer. In essence, conditions on 55 Cancri E would be so harsh and dynamic that they redefine our usual concepts of weather, leaving us to imagine a place of molten flows and ephemeral clouds of vaporized rock. The uniqueness of 55 Cancri E is owed to several factors. First, it orbits extremely close to its star, yet remains only about twice Earth's radius. That alone indicates a highly compressed, ultra-hot environment, unlike anything in our solar system. Second, its potentially carbon-rich composition stirs speculation that enormous diamond deposits might form under intense pressure, an idea that is scientifically plausible under certain circumstances, even if not firmly proven here. Third, the planet resides in a multi-planet system, giving astronomers a chance to observe complex gravitational interplay among multiple planets. Fourth, 55 Cancri itself is near enough to Earth for repeated and detailed observations, allowing for much finer data on transits and radial velocities than many other exoplanets. Finally, the interplay of tidal forces, possible spin-orbit resonance, and unstoppable surface heat might produce a type of extreme tectonics, if any plates or layers do exist in a semi-solid state. The planet thus serves as a fascinating natural laboratory for exploring how super-Earths might be formed, migrate, and evolve close to their parent stars. There are, of course, no immediate plans to send spacecraft to a star system over 40 light-years away. This is far beyond any near-future capability. Nevertheless, astronomers rely on an array of telescopes, both ground-based and in space, to gather every possible clue. The Hubble Space Telescope has attempted observations in the ultraviolet, while Spitzer and Chandra have taken readings in the infrared and X-ray ranges, respectively, aiming to discern something about the interplay between the planet and its star. But the James Webb Space Telescope represents a new level of infrared sensitivity, possibly enabling the detection of extremely fine spectral features related to the planetary atmosphere, or exosphere, if it exists. By analyzing starlight passing through any gaseous layer, JWST might pick up signs of sodium, silicon oxides, or carbon-based molecules in minute concentrations, an outcome that would yield a direct glimpse into 55 Cancri's scorching environment. In the future, improved instruments, some with mirrors over 30 meters in diameter, may similarly refine their detection capabilities. Yet for now, we remain reliant on spectroscopic hints rather than direct close-up exploration. In conclusion, 55 Cancri E offers a vivid reminder that not all planets mirror the baseline we know as Earth. A short orbital period of just 18 hours, a surface temperature presumably hot enough to melt or even vaporize rock, and the suggestion of unusual carbon chemistry stand out as features that would be impossible in our own solar system. Observing this planet gives astronomers crucial insights into the ways planetary systems form and evolve, as well as broadening our grasp of the chemical, geological, and atmospheric processes that can take place across the cosmos. If such a hellish world can remain stable in close proximity to its star, then perhaps countless other systems in our galaxy present even more outlandish conditions. Already, astronomers discuss planets with glass rains, pitch-black gas giants that absorb nearly all incoming light, and cold super-Neptunes that revolve in the dim outskirts of their stars. Yet 55 Cancri still commands special attention. The stark contrasts in its environment, coupled with the notion of diamond layers and the powerful star-planet interactions at play, keep it in the spotlight for observational campaigns. With each fresh look at its transit, each new measurement of radial velocity, we refine our understanding of this extreme super-Earth and maybe the physics behind planets that push the limits of what we once considered feasible. Ultimately, 55 Cancri E underscores how the universe goes far beyond our ready-made categories, creating astonishing configurations of matter, energy, and forces. Who can predict what even more bizarre objects await detection? Every new piece of data about 55 Cancri E might inspire us to explore possible parallels in other star systems, including those that might have kinder environments reminiscent of Earth. But for now, 55 Cancri E stands as a striking testament to cosmic diversity, a crucible of molten stone and possibly exotic geology, provoking us to question just how singular Earth's own path might be. If you find yourself curious about such extreme planets, or have theories as to how a world can survive with such colossal heat and possible diamond caverns, feel free to share your thoughts. Public and scientific enthusiasm for these tormented realms continues to grow, meaning we can look forward to more refined spectroscopic data, surprising results, and perhaps brand new revelations about how planets form and whether life itself could emerge under truly exotic conditions. Let us stay in touch with all the wonders the universe has to offer and anticipate eagerly the next wave of cosmic surprises that is sure to come.